Let's start recording. Yeah. No.
Oh, it has to be.
No, that's extra credit. So it has to be something cool, like on a hat or t-shirt, not on piece of paper. Or you can bring like a big sign, like a banner or something like this. So everyone will make fun of you in school. If you have the Maxwell equation on your t-shirt, you go to a party, nobody will talk to you, right? Yeah, I have it on my hat. No one talked to me. They think I'm weird. It's fine, right? It's nice. Uh, just um just want to come back. This is called what it's a low pass filter capacitor. So capacitor will let AC go. It will stop DC. So it tends to stop low frequency, but it will tend to let go high frequency. Because if you have a high frequency signal, the capacitor will charge, discharge, charge, discharge. So it's like the capacitor is just a short, right? It's just a wire. So high frequency AC, the capacitor is just gonna let go. So if you have a signal here, like a regular signal, but with a lot of noise on top of it, so high frequency signal coming here, the high frequency signal, which is like the noise, will be dumped into the capacitor, and what will be left is the low frequency signal, which that's what you want. This is just an idea how to use a capacitor. If you reverse, then you have the opposite. You're going to have a high pass filter. Okay, it's just a parenthesis here. Make sure you know how to use your equation sheet. So the test is on Thursday. Don't be late. Don't forget, right? Because makeup, it's always harder because I cannot make a makeup that will stick to the practice exam that you have in Canvas. Does not count. But I try to make it as close as possible as the test number 2. So don't miss test number 2. And you see you have all the equations here. So electric potential, that's what you want to use. Make sure you know how to use them. And here you have the capacitance. So again, capacitance only depends on the geometry. It will be the amount of charge per unit voltage. So it's like a beaker. You know how much charges it can hold. This is the good morning electric field between the plates of a capacitor. It's going to be uniform. That will be the voltage across a parallel plate capacitor. That will be the energy that can be stored. This is the density, energy density, so energy per unit volume inside an electric field, whether it's electric field between the plates of a capacitor or even an electric field inside an electromagnetic wave. If you have a dielectric, it's going to boost your capacitance by a factor K. Okay. If you have like dielectric inside an electric field, the electric field will get weaker. Okay, we talked about that, and then you don't have to worry about this. So you have this part and that part. You can also bring the algebra-based equation sheet, which are more simple if you prefer. And you also have a DC circuit, right? Don't forget the DC circuit. Hey, you have AC circuit here, you have circuit there. So you have also those equations there. Okay, let's move on. Okay, so we're gonna start a new unit here, unit 5, which is not in the test. Okay, and we're gonna start with magnetism. Now, with that chapter, which is unit 5, you have another slide. You have other slides attached to it, and it's called Big Ideas. So it's going with it. It's attached to it. In these slides here, so it's called Big Idea. I summarize everything about electromagnetism. So we're gonna switch back and forth between the units that we're gonna cover and these slides here. Because it's like a cheat sheet. So for example, here I start with static electricity. So it means electric field that does not change with time. Okay, you see a positive charge will make an electric field diverge outward. A negative charge makes an electric field converge inward. So that's the source, that's a sink. Here you have a parallel plate capacitor. You see that the electric field is uniform from plus to minus. So typical question for the test, if you put a positive charge here, it's going to accelerate. Okay. If you push a negative charge, if it's an electron with some momentum to begin with, it's going to slow down, stop, and then come back. Okay, so be careful. It could be tricky, right? So it's like if I have a mass in my hand, I give it some initial momentum, it's going to slow down, stop, and then come back. So you have to be careful with the sign. Is the acceleration negative or positive? It's going to speed up or slow down. So be aware for that, for the test. Capacitors, we talk about that. Okay. And then Faraday cage. You cannot have an electric field inside the conductor. You cannot have a charge inside the conductor. However, the voltage is the same. Okay. So if this is 10,000 volts, inside is going to be 10,000 volts. If someone touches it and that person is insulated, not touching the ground, it's going to be at 10,000 volts. These are equal potential. Okay. If he's inside the cage, he's safe because this is a Faraday cage. No charge can get inside, no electric field. Anything pointy here, if you have a conductor which is with a sharp edge, you're going to have a very strong electric field, very willing to discharge very quickly. Okay, so I don't know if it's in the test. This question, conceptual question, is that equipotential are always perpendicular to the electric field. Equipotential always perpendicular to the electric field. Electric field goes from plus to minus. This is the electric dipole. Okay, so it's a review very quick. So for example, here, this is how we make X-ray. You have an electron, so filament can be very hot, electron can escape. It's gonna speed up because here it's gonna be plus. Kinetic energy, so potential energy. Definitively a question about that. Potential energy, electric potential energy is the charge times the potential, QV. V is a property of 2 points, so it's a voltage difference, right? So QV equals the change in kinetic energy. All that kinetic energy is going to turn into X-ray. Okay, talked about that. Use in linear accelerator. That's used to be linear. Now they make it curved with a magnetic field. Used to be linear. You can accelerate particles and you're going to smash them together and you have new stuff. New subparticles. So these are equations that we have been using. This is Coulomb's law. An electric field is the force per unit charge. Okay, you have this relationship between the electric field and the voltage. Remember, the electric field is the slope of the voltage. Definitively a question about that. If you have an electric field, if you have voltage equipotential and the equipotential are very close to each other, it's like contour line that even the slope is large, the electric field will be large. Larger is the slope, larger is the electric field. Electric field is the slope of the potential. Okay, electric potential energy, it's a different equation. Okay, so if you have a distribution of charges Q1, Q2, Q3, okay, then you can compute the electrostatic energy of the configuration, not at a given point. Voltage is the energy, potential energy at a given point relative to very far away. The electrostatic energy is the total energy of a configuration, like the water molecule. So you can go back to the slide and see how, I think there was one question about that, how you can do the computation. Electric potential is a scalar field. Okay, so it's a property of space at a given point, how much potential energy relative to far away where the energy is zero. Okay, magnetic field. Okay, go back. I go back. So this is not on the test. So about magnetism, you all know this is a permanent magnet. You always have a north pole and a south pole. So that's called a magnetic dipole. Even if you have a permanent magnet, always a north and a south. If you break a magnet, you're still going to have a north and a south. And you break it again, you're going to have a north and a south. And you break it again, you're going to have a north and a south. So you cannot have a monopole. Doesn't exist. Okay? So it's not like electrostatic. In electrostatic, you have a proton on its own, so it's a monopole. You can have an electron on its own, it's a monopole. And you can have a dipole, an electric dipole, a plus and a minus, like a water molecule. Magnetism, no such thing. If you find a monopole, you get the Nobel Prize, and then you will remember me, right? You cannot have a monopole. So far, no way. Okay, north and north repel, south and south repels, north and south attract each other. So we know about in the Western world about magnetism with the Greek, 600 BC, about the so it's they reported about it, so they knew about it. So the story goes that some shepherds, when they went into the field, they noticed that little pieces of a mineral here that they call lodestone, it's magnetite actually, was sticking to their shoes because the shoes was made of nails, because it's Greece is very mountainous, so they had to climb up the mountain. And these are called magnetite. We call them magnetite later on because it comes from the Greek word, which means magnesia, which is a region in Greece. Okay, that's already 600 BC. And later on, it was used. So this is a mineral. If you take an earth science class, sometimes they have you identify minerals like feldspar and granite, and magnetite is one of them. And you know it's magnetite because it can attract iron or paperclip. Okay, so that was, and then it was used by the Chinese to make compasses. Okay, and then the first time, so we think that even in the 13th century, this guy wrote about magnet. I forgot who he was. Maybe Italian. I'm not sure. You can Google him. But the first time it was really in a book. Okay, that was a book written by William Gilbert, very famous. He wrote about magnetism. Okay, and he did many experiments about magnetism. And he was so famous because he was a physician of what's this very famous queen? Yeah, Elizabeth I, right? It's a great story. I don't know if you like story, but she was the daughter of Henry VIII, very famous king of England. He's very famous because of his 6 wives. Divorce, what it's called? It's divorce, beheaded, died, divorce, beheaded, survived, right? Not an easy guy to be around, but the last one was lucky, right? She survived. And the story is that England used to be Catholics, right? It was a Catholic country, and then and he wanted to divorce, and you don't divorce. So if you are Catholic, so he changed the religion into Protestantism, right? To be a Protestant, then he could divorce his wife, but then it turned very bloody because after his daughter Bloody Mary took over. That's why she's called Bloody Mary, because she Bloody Mary because she killed so many people. Okay, this is totally a tangent. Let's come back. Very interesting story. Okay, so that's her, his daughter Elizabeth I. Her mom got beheaded by her dad. So anyway, he was the one who understood that Earth is behaving like a giant magnet. He's the first one to understand that. And I can show you a simulation. Can tell you the traumatism, right? The mom beheaded by the dad. It's not very cool. So this is a bar magnet. And the first thing to remember is that a magnetic field always curve, okay, always curling around. An electrostatic field, so an electric field which is static, not changing with time, always diverge or converge. A magnetic field, whether it's changing with time or not changing with time, always curves. Okay, and there is an equation for that, vector calculus. You can find how much curling you have in a vector field. So a magnetic field always curves because you do not have monopoles. So the magnetic field goes out of the north, curves around into the south, back to the north. So you can, these are compasses. So a compass is actually a magnet. This is the north and this is the south. So you see that the south is attracted to the north. Okay, and I can move the magnet around. So north is attracted to south. Okay, so out of the north into the south, always curling. Okay, so you can imagine. So this is to visualize the magnetic field. So the same way you have an electric field, you're going to have a magnetic field. It's a vector field. So anywhere in space, you can define a vector with a direction and a magnitude. So you can visualize it with these little compasses. You can imagine these are little compass, little magnet. Okay, and the red part will be the head of your vector. So imagine this is a vector. Okay, so this is the head, and that will be the tail. So how do we do that? We use something called iron filing. So we sprinkle all around the magnet little pieces of iron that get magnetized. So they turn into a magnet. There will be a torque applied to them, okay, and they will align themselves with the magnetic field. It's touch screen. Okay, so it's very much like visualizing the electric field with little seeds. Okay, any question? We good so far? Okay, so these are little vectors. You can think of them as vectors. Now, if you take the Earth, everything happens like there is a big bar magnet. So the Earth is behaving like a bar magnet. And if I take my compass is going to show me, of course, the geographic north. That's what you expect from a compass. But north attracts south. So the geographic north is the magnetic south. Surprising, right? Maybe you knew that. So geographic north is a magnetic south. If you go the opposite here, you see the south is attracted to the north. And again, a magnetic field curves. It's like a vector. This is the head. This is the tail. Out of the north, boom, 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 curling around into the south, back to the north. So it never, ever diverge or converge. Okay. So what's actually happening here, we will talk about that later, but the Earth is like an electromagnet. So inside here you have the core. The core is solid because you have a huge pressure. Even though it's very, very hot, the pressure is so huge that it cannot turn into a liquid. But then you have the outer core. So the outer core is partially liquid. Okay, and we don't really understand how it's working. We have like an idea, but we don't know the details. But it's moving, and it's made of nickel and iron ions. So ions that have lost 2 electrons or 3 electrons. So it's charges moving inside the Earth. So it's like a current. It's like electricity, right? You have current flowing inside the Earth, and each time you have current flowing into a loop, that's an electromagnet. It will behave like a bar magnet. Okay, so that's what's happening. Okay, so an electromagnet, each time you have a loop of current, okay, and it's gonna make a magnetic field. Okay, so this one will be the north, you see, because it's showing you it's like a vector out of the north into the south. So that's happening inside the Earth. Okay. picture. So the magnetic field of the Earth has a function. It's very important for us because you see it's shielding us from radiation coming from cosmic radiation, from the sun, from space. You have a lot of charged particles such as protons or electrons, very dangerous, right? If you're exposed to too much of them, you can develop cancer. It's not very nice. Cosmic radiation not very nice. Thanks to the magnetic field of the Earth, those radiation will be trapped inside the magnetic field of the Earth. So it's protecting us. Okay, so it's so now I have a but this picture is good enough. Come from the sun, mostly the sun. That's why this is day and this is night. Okay, and most of the planets, all of the planets, they have also magnetic field to protect them. Guess now let me show you a simulation. Just have to remember. Come on, come on. No, that's not the one. Okay. That's what's happening. So when you have a proton coming from the sun, for example, it's the magnetic field of the Earth will make it go into a circle. Okay, so you're gonna learn that an electric field accelerates a charged particle, but the magnetic field does not make it go faster or slower. What it does, it make it go into a circle. It will deflect it, right? So a charged particle coming from the sun will be trapped here. It will be forced to go around and around and around and around. It's still an acceleration because you are making a turn. Okay, there is a centripetal force, and because there is this acceleration, but the centripetal acceleration, it's going to lose energy. That energy is going to go into light. Okay, so it will be called the Van Allen belt. But you see, it's protecting us. You have only two places where it's not protected, fully protected. You see those places? North Pole and South Pole, right? So what happens here is that the charged particles coming from the sun will interact with the atmosphere, oxygen and nitrogen. Okay, it will kick the electrons, and the electrons, when they come back to their energy level, they're going to burp out light, which is the northern light. So they say, it's safe. But I had someone from, I don't know, uh, what's it called? Some east, north countries over there where you can see the northern light, Finland. And he said that usually they told them not to go out too much, not to chill out too much when you have the northern light. So I don't know. But that's the story. Okay, so these are called the Van Allen belt. You can see it's along the magnetic field line. So again, when you have a charged particle coming from the sun, it's going to be trapped here. It's going to go around and it's going to burp out light. So that was seen for the first time by the Americans during the Cold War when they started to go in space. And so they called that the Van Allen belt. And I'm sure you all seen northern light, right? Yeah, those. Okay, it's because the charged particles, there is no magnetic field to trap them, so they interact the atmosphere, and you have those beautiful light. When the electrons come back to their energy level. Okay, what else? Well, now I'm lost. We don't want to watch that movie, it's too violent for you. Okay. Okay, so a magnetic field is in 3D. Okay, because we always see 2D, but actually it's 3D. And again, out of the North Pole, circle around back the South Pole, and it makes a circle. You can see that we use again this notation, the lines. When the lines are packed together, that means a strong magnetic field. When they are further apart, that will be a weaker magnetic field. So here at the poles, you see the lines are packed together. That means very strong magnetic field. So usually you use if you use a piece of iron, if you have a magnet, you don't leave it this way because it's going to lose its magnetism. Inside those magnetic field, you have energy. There is a energy density proportional to the magnetic field square, so you are losing energy. So you need some guard. So usually you put a paper clip or a nail here, and what it will do, so it will be attached to the magnet, it's going to squeeze the magnetic field, and it's going to keep it close to the magnet, and you are not losing magnetism. Okay. Magnetic field here. So this is a horseshoe magnet. Okay, so out of the north into the south, between those two poles, it's almost a uniform magnetic field. So it reminds you capacitor, parallel plate capacitor. Okay, magnetic 3D physical exploration. Okay. I had demo, but I don't know. I'm gonna just go really quick over them. First of all, I don't like to hear myself. I don't like that. So this is a bar magnet. Okay, south and north. I talk too much, but you see, you see what's happening here? It's a force at a distance. And what's happening is that it's the two magnetic field interacting with each other, pushing each other out. Okay, so it's not really a force at a distance, like one is pushing instantaneously the other one. It's just the two magnetic field interacting with each other. And all the special relativity developed by Einstein came from electromagnetism. He was playing, when he was a kid, he was playing with magnets, and then he picked up on Maxwell equations. And out of those four equations, he developed the special relativity and the general relativity. You see, it's at a distance, right? So the two magnetic fields interacting with each other. A compass is a magnet, or that will be the south, that will be the north. And you see, south, north. No monopole, doesn't exist. Look for it, and you will get the Nobel Prize if you find it. Okay, and this is a horseshoe magnet. Again, north and south. You can play with a magnet, you can do a levitation. Okay. So again, if you sprinkle little pieces of iron, you're gonna have what is called a magnetic dipole. So it will behave like compasses, and they will align themselves with the magnetic field. Okay, you can do that here. So this is like a vector out of the north into the south. Okay, Earth is behaving like a bar magnet out of the north into the south. A magnetic field always curves, never diverge or converge. Okay, that will be only a static electric field. So magnet here, north and south, you see that the two magnetic fields interact with each other, and what they want is to bring them together. right? It's like a aura between them, and he wants to bring them together. So this is also a magnetic dipole, exactly the same configuration. So you have a nice symmetry with an electric dipole out of the plus into the minus, always from plus to minus for an electric field. Okay, so north and north repel each other, again interacting through the electric field, pushing each other. It's like two negative charges here repelling each other through the field. The unit for magnetic field is the Tesla. So the Earth, the magnetic field of the Earth is very weak, but it's still enough to protect us, is 0.5 times 10 to the negative 4 Tesla. Or you could say that 1 Tesla is a very, 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 very strong magnetic field. That will be better to say. So 10 to the negative 4, that will be 1 Gauss. Okay, so it's subunit. 1 Tesla is 10,000 Gauss. So 0.5 Gauss. Okay, usually the magnetic field, like a bar magnet, it's going to be very weak Tesla. MRI machine, 1.5 Tesla. It's a killer. It's a very strong magnetic field. And if you work like in a hospital for a job, you learn that you have to be very, 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 very careful, because you had horrible accidents happening. If you have a tank inside that room and you turn on that MRI machine, it will suck the tank inside, and it killed a little boy back then, like a few years ago in New York. So I have to be careful. 1.5 is very, 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 very strong. Okay, a lot of application in environmental science or biology. So those, what it's called, lobsters, many animals like turtles or birds, maybe us. They have little magnetite, iron oxide in their brain that will align with the magnetic field, so that way they don't lose their way. And they did an experiment where they disrupt, like they put an external magnetic field, and those poor things got lost. They went too far away from the shore, because they are not supposed that they use a magnetic field to make sure they don't go far off. They have to stay close to the shore. So they disrupted them. I don't think that was very nice, but I guess it's for the sake of science. That's from the Frost Museum. You see, they explain turtles the same way. Okay, they have some magnetite inside, and they use it to find their way. And birds too. Okay, how am I doing? Where I am? Okay, so 19th century for physics was big discovery, back to back, back to back, back to back. Discovery of the electron with the vacuum tube, discovery of this and discovery of that. And 1820, you remember that at the beginning of the 19th century, you have the battery, Volta. Alexander Alexander Volta made the first battery. So they at the time they were all excited. They did so many lectures for the public, doing experiment just with a battery and a wire connected to the battery with some load. So it was a lot of physicists were giving lectures about them. That was the case of Christian Ørsted. So he was Danish, and on his desk he had a wire connected to a power supply. So current was flowing from plus to minus, and he was demonstrating. And by chance, just by chance, he had a compass on the table, and all of a sudden the compass moved. So what do you think it means? Huh? So there is a magnetic field somewhere, but there is no magnet. There was just a wire with current flowing. So what do you think it means? Yeah, exactly. He just discovered that electricity creates magnetism. The source for magnetism is actually moving charges. Okay, it could be moving electrons, but inside the Earth, it's moving ions, like iron that have lost electrons. So it was a big breakthrough because until then, they thought that you have magnetism, so static magnetism or static electric field or electrostatic. They had no connection between them. And all of a sudden, they found a connection. So that was a big, big, big breakthrough. Okay, so electricity is the source for magnetism. Electricity or moving charges create magnetism. So it's a very famous Oersted experiment. Now we have to experiment with our right hand because you have right hand rules that we have. I want to see my email 1009. I have to cut that. Okay. So Oersted experiment. Here it is. Okay, it's a very nice simulation. So electricity is flowing from plus to minus. So it goes through here from plus, and then you have a wire, thick wire, and the wire goes, the current goes into the board. Do you agree? Do you see that? Are you with me? Okay. You see that the magnetic field of a wire is going to circle around. Very close to the wire, you see the magnetic field is going to be the strongest because the lines are packed together, and then it gets weaker. Okay, but it's on just showing you, but it's in 3D. Okay, so if I go, um, okay, you have to imagine this, right? So it's really circling all around. Okay, so that will be the magnetic field produced by a straight wire. We call that a current carrying wire, circling around. That takes me to the right hand rule number 1. So first of all, remember a compass is like a vector. This is the head, this is the tail. And you see, it has a direction. The magnetic field, every point in space, you're going to have a vector. That will be the vector magnetic field. So take your right hand. You all have a right hand. Okay, that you have 3 rules. First rule, this is the current. Your thumb is the current. Magnetic field will go around like this. Okay. If it's a moving positive charge, if it's a negative charge, you take your left hand. Positive charge current is made of positive charges because of Benjamin Franklin. This is the current is going to curl around. So if I look at the screen here, the current is going into the screen. The magnetic field is going to curl, which is thank you. Right. So if I do it here, it will be counterclockwise. So negative charge will take the opposite. Electricity is going into the board. Magnetic field is going to curve around this way. Okay, so that will be the first right hand rule. The current magnetic field goes this way, and my arm hurts. Now you see that if I switch, you see, now the current is going towards you. So the current is going towards you, out of the board, so the magnetic field is going counterclockwise. So very important for conceptual questions. Are you with me? Okay, now use your head, imagination. Imagine that you take this wire. Do you see that wire? Okay, imagine you take this wire. So you have this wire, right? And the magnetic field is going around. What do you think is going to happen if I make a coil? So if I take the same wire, right, and I do this with it, it's called a solenoid or a coil. If I make a loop of current with many loops with that wire, look at it and imagine what's going to happen to the magnetic field. Do you see it? You don't look at me. Look there. Take the wire and make loops and loops and loops and loops and loops. The magnetic field is following, right? So what you're gonna get? You get something like this. This is an electromagnet. It's an electromagnet, and it will behave exactly like a bar magnet. So if you take a wire carrying current, right, so with moving charges inside, and you make them go around and around and around and around, that's called a solenoid or inductor or coil, right? And it will behave like a bar magnet. This is what we call an electromagnet. If in addition to that, you take a piece of iron, soft iron usually because it works better, and you shove it inside. So you put a soft iron inside. What it's going to do, it's going to squeeze the magnetic field inside. So it will stop the leakage because here you are losing some magnetism to space. So now if you put inside a piece of soft iron, it will squeeze everything inside, and you're going to have a very strong magnet that you can control. When you open the switch, magnet stops. Close the switch, magnet is on. So you can move stuff, like you can pick up like a junk in a junkyard and turn on the magnet, move them, and then let go. So this is called an electromagnet. Okay, and there is another rule. So this one will be what? This is north, so this one will be what? Which? North or south? South. Okay, south attract north, and this one will be north. I will go back to that. But rule number 2, do you still have your hand? Hopefully everyone has a hand, right? So if you coil, if you have a coil, so if you have current going into a circle, that will be the north. If you have loops, that's going to be the north. So in that case, north is here. This way, this way, this way. That's going to be the north. My thumb is the north. I can do the same thing here. So that's the second rule for the right hand. So electricity is flowing this way, this way, this way. The thumb here, it's going to be the north. So that's going to be the north pole, and that's going to be the south pole. So it's opposite, right? First rule. This is a straight wire that will be the current magnetic field curves around. Second rule, the current goes this way, that will be the north. It's called the magnetic dipole. That's the north, and that's the south. Okay? So if you switch, it's gonna switch. So now it's gonna be the south, and that's gonna be the north. And again, magnetic field goes out of the north, curves around into the south. So if you are, so for this unit, electromagnetism, it's really distinct between the concept and the math. Once you have the concept which are not intuitive, you really have to understand them. The math is just the math. Concepts are not that easy, so that's why you really have to understand the concept. So again, if you have a straight wire, magnetic field will curl around. That will be the first right hand rule. Okay. If you have a curling current, so if it's a loop, okay, if you have a loop of current, then that will be the north. Okay, so if you have a loop of current, you can do it here. Take your hand. I'm looking at this one here. This is the loop. Loop, loop. Up, up, up is north. Down is south. See? Loop, north, south. So this is the north and this is the south. Magnetic field goes out of the north into the south, always looping around. It's a curve. Okay, in vector analysis, vector calculus, it's called the curve. The magnetic field is always curling. It's behaving like a bar magnet, out of the north into the south. Is that clear? Okay, application, an electromagnet. So here is a demo you can do for extra credit, very easy to do, but you need a nail made of iron. If it's like another type of nail, it doesn't work, it has to be iron. Then you go around like this with a wire. The wire should not touch if it's not insulated. If it has some insulation, then it's good. Better it is. You don't leave it this way too long because you have a short, so it's going to be very hot and the battery is going to lose everything. Best is to use a 6-volt battery because you have a lot of current, and then you can pick up paper clips, right? It's an electromagnet. That's how an electromagnet works. I have the demo. I did a long time ago in another life. Okay, so for typical conceptual question, you see, so this one, you see, if you use a 9-volt battery, it doesn't work very well because 9-volt battery has 9 volt, but not enough current. If you have a 6-volt battery that you buy at Walmart, it's for camping, whatever it's used for, you have more current, so it works better. So I tried this experiment. At first, it didn't work because I had a 9-volt battery. So here's the experiment, typical question on the maybe test or not two, but or pop quiz, is that if I make it a line, so this wire is aligned with the compass. When I'm gonna close the switch, the compass is gonna turn until it's gonna be perpendicular to the wire because the magnetic field is curling around. Okay, it's doing this. So I'm going to try. It doesn't work. I'm not happy. So now it's going to work. Ready? So this is a 6-volt battery, lot of current. And close the switch, close the switch. Thank you, thank you. Close the switch. Boom. You see that? You can do that experiment, right? Larger the current, better it is. But again, it's a short, so you have to be careful. And then I made an electromagnet. I talk a lot, so I'm not going. So I took a screwdriver here. So this wire has some insulation. It's like enamel, like a varnish, right? So otherwise you cannot do that because if they are touching and it's not insulated, it's not going to work. You need loops, 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 loops. And it turns into a bar magnet. Blah, 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 blah. I talk too much. Okay, okay. So here is my bar magnet. And you can pick up paper clip. Huh? Isn't that cool? If it's good design, when you turn off the switch, everything falls. And now you can see with a compass, you can see that will be the north, because south, south and north. So there is a north, and that will be the south. And this is also a bar magnet, electromagnet, blah, blah, blah. You see, so cool, very nice. Okay, this is more professional, but I broke it. Okay, so you have a solenoid. Inside here, you have a core, soft core inside, and it will squeeze the magnetic field and force it to stay inside, like the screwdriver. So I'm connecting them to the power supply. So there is a core inside. You see, it's a piece of iron. And it's going to be super strong. Close the switch. Super strong. So more loops, we're going to see that the magnetic field of the solenoid is proportional to the number of loops per unit length and the current. It's about uniform inside, constant. It depends on the density of loops, how many loops per unit length, and the current. Okay, and okay, and you have a baby one here that you can use to make a ring a bell. Ring. Okay. Not taking a tangent. Okay, so let's see if I have other videos.
Plastic, and all you're gonna do is gonna take my iron filings and sprinkle them onto the.
See, these are the iron filing.
You will see that magnetic. This is the same thing, except now I'm doing the two compasses that I have inside the coil. You can see now the compass needle is basically running perpendicular to the ring. The coil, this is the coil, the compass needle is perpendicular to the coil. It's only switch to turn my current on, then the torque turn into, as soon as I start checking the switch, then the compass needle react to the magnetic field that produced by this coil. Now they're lining themselves up parallel to the coil because that
Okay, and so that's a solenoid, right? You have seen that maybe in the lab, and that's the soft core, soft iron core inside, and it will boost the magnetic field, right? So it's going to squeeze it, force it to stay inside. Okay, same thing here. So the magnetic field, a solenoid is when you have many turns per unit length. And you see, in that case, the magnetic field inside is uniform. We're going to neglect everything outside. And it's proportional to the current and proportional to the number of loops per unit length. So you have that in your equation sheet. That will be the magnetic field of a solenoid. Okay, what else? So this is in another life also. I did that experiment. I have my solenoid, connect that to a power supply, sprinkle it with iron filing, and you can visualize the magnetic field out of the north into the south, circling around. And inside, I shove like an iron. You can do that experiment. Everything is cheap today. Like you want to buy a solenoid, it's very cheap. Hey. Okay. Okay. So something interesting for you is that when you're going to connect a solenoid to a power supply, the magnetic field will not pop up like this, right? Not instantaneous. It's going to expand until it's reach its maximum value. Okay, this is because there is some resistance, there is some inertia. So the magnet, the solenoid, it's gonna resist the expansion of that magnetic field, but at the end it will reach the maximum value. But this is called an expansion. You see, you have loops here. The magnetic field is gonna expand, so all the energy that you are using from the power supply, it's going to be locked inside that magnetic field. So the same way a capacitor is a way to store energy from the power supply inside the electric field, the magnetic field is storing energy. That energy, okay, when you open the switch, that energy is going to be burnt out as a very high voltage. With a capacitor, that energy, if you open the switch, if you discharge a capacitor, this energy can be burnt out as a very high current. So anyway, you are storing energy inside the magnetic field. And when you open the switch, let's say, open the switch, you see the magnetic field is going to collapse. We talk about collapsing, right? The magnetic field is going to collapse, but it's going to take some time, which can be very dangerous because sometimes you are using appliance and you open the switch and it's still going to be, it can make a spark because of that solenoid. It's called an inductor. So both capacitors and inductors, they can burp out energy. Capacitor will be high current, inductor will be very high voltage. But it's the current that kills, right? Depends how much current you have. Okay, so that's good, blah, blah, blah. So remember that we have like a sidekick here. This one, okay? It's called Big Ideas. And I try to summarize everything. So, for example, here, even those neodymium magnets, very strong magnet, always have a north and a south, out of the north into the south. This is to visualize the magnetic field, so it's going to be in 3D. Okay, so we talk about that, interacting with each other through the magnetic field. Okay, you can think of this like a little vector. It's a vector magnetic field, always tangent to the magnetic field lines. Okay, the same way you have an electric field here, uniform electric field between the plates of a capacitor. It's almost uniform here between the poles of a horseshoe magnet. You use little seeds here, okay, to visualize the electric field, and you're going to have a torque applied to those little seeds here. Okay, it's going to be polarized. You're going to have a plus and a minus, and it will rotate. Those little seeds will rotate until it's aligned with the electric field. Same thing here. Those little iron filing will rotate. So it's going to be a torque. There will be a torque applied until they align themselves with the magnetic field. So it will turn them into a magnetic dipole with a north and a south. Okay? After the experiment, if you have a straight wire, that's the first right-hand rule. The current is your thumb, and the magnetic field will curl around. So this is why we have the magnetic field around the Earth, because inside the outer core, and it's not fully understood, you have ions, nickel and iron, and they are moving. So it's behaving like an electromagnet, but again, it's not fully understood how it works. Geographic north is the magnetic south. Okay, are you with me? Not spacing out? Okay, so shielding us, magnetic field of the Earth. Source of magnetism is electricity, so you can use electromagnet here because you you control the magnetism. This is a very strong electromagnet here. So each time, so this is the other rule, right? So if the current is going this way, the thumb here is going to be the north. Okay, that's what I'm going to show you here. Curve, thumb is the north. So that will be the north, that will be the south. This way, going this way, this way, this way. So that's going to be the north and that will be the south. And this is an experiment you can do. And don't leave it this way because it's a short and it's going to be very hard. But you can do that experiment. The way they do it to make a uniform magnetic field when they are doing experiments in the lab, it's called Helmholtz coils. So you have two loops here, two loops of current, and that the distance between them, the distance between them should be equal to the radius. But if you do that configuration, then you're gonna get a uniform magnetic field, and you can do experiment with them. You also have an experiment, because that's the way to have exactly that equation here. Because if you make them too close or too far away, of course you're gonna have a magnetic field, but it's not going to be uniform like this. So it will behave like two parallel plate capacitors, with a uniform electric field. So maybe you do that in the lab. Maybe you have seen that in the lab. Okay. Always remember, an electrostatic field diverge or converge. A magnetic field doesn't matter if it's moving with time, not moving with time. It's always curling. We're going to see that an electric field that is changing with time will curl as well. But a static electric field diverge and converge. A magnetic field always curls. So, for example, if you have something which is not turned on, you still have charge carrier, so electrons, free electrons. And so you're going to have an electric field even if it's not on. No magnetic field, okay, because the charges are not moving. You need to have a moving charges to have a magnetic field. Once it's turned on, so then yes, you're going to have an electric field and a magnetic field curling around. Cannot be healthy. Okay, so I go back to here. No, I go back to here. No, I go back, I don't know where I am. I should be here. It's the same thing. Okay, application MRI is a huge electromagnet. This is an electromagnet. Okay, these are electromagnet speakers here. You can do that experiment also. It's gonna, that coil here is gonna behave like a magnet. And because this is AC, so the current is gonna go in one direction, the other direction, one direction, the other direction. So the magnet, the electromagnet here will go north, south, north, south, north, south. So it's going to oscillate at the same frequency as the current, and it's going to push and pull a cone, this cone here that will be pushed and pulled at the same frequency. So it's going to be a sound at the same frequency. So that's how we make sound with a speaker. Okay, I don't know if I used to have a demo. No, don't talk. No. Do you see something with the speaker? Yeah, thank you. Okay. If you connect that to a power supply, Wait, 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 wait. Okay, okay, connect, connect. Connect here. You, I don't know if you can see, but it's moving. It's moving at the same frequency that I'm doing like a mechanical switch on, off, on, off, on, off. So the cone is moving. Okay, so that's how a speaker works, right? You have the current flowing AC back and forth, and it will push and pull the cone at the same frequency, and you're gonna have sound wave at the same frequency. So William Sturgeon, so that was in 1860 something. Forgot the date. I don't know. 1825. 1825. He made the first very, very strong electromagnet that could lift 90 pounds. So it's very strong. So physicists, they come up with a new uh, breakthrough, and then you have engineers, they improve them. They improve the experiment for some practical purpose, right? So at the time they didn't have rubber, so they used some kind of fabric to insulate your electromagnet. So you can Google him and learn about him. Okay, someone complaining. Okay, how am I doing? Good. Okay. Third right hand. Okay, so electricity, so a current will create a magnetic field. So if you place a current inside a magnetic field, it's like you place a charge inside an electric field, it's going to be acted upon by a force QE that will accelerate the charge. So it makes sense that if you place a charge inside the magnetic field, maybe something is going to happen. But that charge has to be moving. So if you have a current inside a magnetic field, you're going to have a magnetic force because both magnetic field will interact with each other. So the wire, the moving charge, okay, will be acted upon by a force, a magnetic force, but that force will not accelerate the charge, it will deflect it. Okay, so if you have a moving charge inside the magnetic field, it's going to be deflected. That takes us to calculus again with the cross product. Okay, so if you have two vectors, you can dot the vectors A dot B, or you can cross the vectors. So if you see my hand here, if you have the vector A and the vector B, okay, and they don't have to be perpendicular to each other. If you cross them, you're going to have the vector C perpendicular to A and B. So let's do this first. Okay, take your right hand. Ready? Another one. Okay, like this. So that's going to be, let's say, this is your current. That will be your current. The thumb is the current. Agree? The palm here is going to be the magnetic field. Magnetic field. The force is going to be out, like growing out of your palm. So you have three vectors. The current is a vector because it has a direction, the magnetic field, and that will be your force. Okay, so let's apply. The magnetic field goes into the board. No, the current is going into the board. Do you agree? The magnetic field goes this way. So the force is down. Down. You have three ways to do it. I'm just showing one of them. Okay, so again, right hand, the current is going into the board. My magnetic field is going this way. the current is going down, out of your hand. Okay? It's called the right hand rule. It's for the cross product. So you are crossing I, B, and you get the force. I, B, and you get the force. Okay? I like to do it this way. Now, you can do it this way as well. That's another way to do it. Okay? So, for that to work, for that magnetic force not to be zero, the charge has to be moving, and you need to have a perpendicular component of B perpendicular to the current. So here I have a nice example. Here, again, take your right hand. So the current is going this way. The magnetic field is going to the right. So the angle doesn't have to be 90 degrees, right? This angle doesn't have to be 90 degrees. So the force is coming out of your pole. Okay? If they are parallel to each other, there is no force. Okay, so if this is the angle between B and I, if this angle is 0 degrees or 180 degrees, there is no force. Maximum will be 90 degrees. This is called the cross product, and that will be the equation for that. Most important is to know how to use your right hand. The current, magnetic field, the force is coming out of your hand. Okay, so what's the equation? The magnitude is the current times the length of the wire inside your magnetic field times the magnetic field times the sine or the angle between the magnetic field and the current. Is that clear? It's a very nice slide. Example, typical experiment here. You have your magnetic field from north to south. So let's see, the current is going towards you. Toward you, magnetic field is going down. And so the force is going to the right. You don't have to distort yourself like me. I'm sure there is a different way to do it. But that will be the force going this way. Okay? So I have a nice... is that this one? No. Uh, safe. Someone safe. I just need to find the simulation. I think it's the other one. Ah, okay. It's called a current carrying wire. So predict here. Where do you think it's gonna go? So the current, where is the plus? The plus is the blue. I don't know why. Plus is blue, so it's gonna go this way. So it's gonna this way. To the right. To the right for me. Okay, so plus goes here. So the current is going this way. The magnetic field is going down. So which way it's gonna move? My hand hurts. I don't know. To the right. So which way? To the board. Let's see. Yeah, see that? Agree? Okay, because the current going this way, north, south, the force going into the board. If I switch the battery, uh, close the switch, now it's going to be the opposite. And switch the magnet, opposite. Okay, so the magnitude will be the length of the wire inside the magnetic field times the current times the magnetic field and the sign. Okay.
Here and there. Right. Through these here, electricity go up through the sky, through the ground, through the copper tube, and then up the ground, and then back home. So going this way, drag field going up, we expect a force input. Now, if I reverse the direction of the current, we expect an output.
Isn't that cool? I don't know where that horseshoe magnet went. It's like from the bottom of the ocean or something. So this is a horseshoe magnet, very, very strong. It's for demo. So the current, so the force has to be up or down because they are perpendicular to each other. Okay, always perpendicular. That goes up. That's cool. I had another one. Oh, that was another life. Another life. Ah, don't talk. So you see, you have a magnet, permanent magnet, and here you have a bulb. But the bulb is connected to the outlet. So you're gonna have AC. So the current is gonna flow in one direction, another direction, one direction, another direction. So the wire inside is gonna be pushed and pull and push and pull. So it's going to oscillate at the same frequency as 60 hertz, right? You have 60 hertz from the outlet. Isn't that cool? Oh, and I lost another life. Okay, and again, if you go to big idea, I show you. That's one way to do it. Okay, the current, the electric field, that will be the force. That's called a cross product. Or you can do it with your right hand this way. Current, field, force. And then there is a third way. So you pick your way. Okay, you have different ways to do it. So you have all these right hand rules that I try to summarize here, slide 17. Okay, so that will be the magnitude. Again, it's a cross product for those who are going to take calculus 3 or 4, whatever. Vector A, vector B, that will be vector C. You are crossing the vector A and B to get C. But the angle, if it's 0, nothing, it's going to be 0. If it's 180, it's also going to be 0. Okay, so again, same thing here. You can practice. The current is going towards you. Magnetic field is down, so the force will be perpendicular. Okay, let's do. We're gonna do the pop quiz. Let's try this one. Conceptual question. Which way it's gonna go? So the current is up. The current is up. Where is the magnetic field? Magnetic field cross means into the board. So current is up, magnetic field is into the board. Where is the force? Right, left, right, and that will be right, right. So when you see a cross means into the board because it's like an arrow and you are seeing the tail. Okay, in that case, the current is going towards you and the magnetic field is into the board. So they are anti-parallel. Is there a force? If it's parallel or anti-parallel, no force. Because it's going to be the sign of 0, or in that case, will be sign of 180. So no force. No force. It needs to have some perpendicular component. And what about here? So it's let's see, the current is going towards you. Magnetic field is going to this way. Current this way, magnetic field going this way. So the force will be up. Very good. So up. So if you want to balance gravity, you're gonna use this one. Gravity is gonna go down, and the magnetic force will go up. The force magnetic force will be down, gravity will be down, so it's not going to work. So the answer is C. Okay, so unit Tesla means Newton per amp meters. So Tesla, 1 Gauss is 10 to the negative 4 Tesla. And these are easy, so we'll do that next time. You have a pop quiz with a lot of